Hi, everyone, and welcome to this course on SerDes Basics. My name is Bradley Cecil, and in this series, we're going to build an intuitive understanding of how high-speed serial links work, what problems they solve, how they're structured, and how we design them to reliably move data at very high speeds. Modern computing systems move enormous amounts of data, whether it's a GPU rendering graphics, a CPU coordinating tasks, or a network switch moving packets, the demand for bandwidth continues to grow every year. At first glance, the solution seems simple. If you want to move more data, just add more connections. Send more bits in parallel, and your bandwidth increases. And for a while, that approach worked well. Imagine you have 8 traces on a printed circuit board, and each trace carries 1 bit at a time. That means you can send 8 bits per clock cycle. If you want to double your bandwidth, you could just add more traces, go from 8 to 16 or 32, or even more. Conceptually, it's straightforward, but in practice, this approach runs into serious problems as speeds increase. The first problem is physical area. Every trace you add requires a physical pin on an integrated circuit. Pins take up space, increase package cost, and complicate routing on a board. You can't keep increasing pin count indefinitely. There are practical and economic limits. The second problem is timing mismatch, also known as skew. In a parallel system, all the traces are supposed to carry bits that arrive at the same time. But in reality, signals don't travel perfectly in sync. Some traces are slightly longer or experience some form of discontinuity, which cause different delays. At lower speeds, this isn't too much of a problem, but as you push the data rate higher, those small timing differences become significant. If one bit arrives just a little too late, the receiver might capture the wrong value. Even if every individual trace is behaving correctly, the system as a whole can fail because the bits are no longer aligned in time. The third problem is power. Driving many traces at high speed consumes a lot of energy. Each transition requires charging and discharging, and when you multiply that across dozens or hundreds of traces, the power adds up quickly. So while parallel interfaces are simple and effective at low speeds, they do not scale well to the very high data rates required by modern systems. This is where SerDes comes in. Instead of sending many bits at the same time across multiple traces, a SerDes system sends bits over a single trace or a small number of traces, but at a much higher speed. This process is called serialization. A block of parallel data, such as an 8-bit or 16-bit word, is converted into a high-speed stream of bits that are transmitted sequentially. On the receiving side, the process is reversed. The incoming serial stream is captured and reconstructed back into parallel data. This is called deserialization. That's where the name comes from. Serializer and deserializer gives us SerDes. The key idea here is that we trade physical real estate on the PCB for speed. Instead of increasing the number of traces, we increase the transmit speed on each trace. If you think about bandwidth as bits per second, there are 2 ways to increase it. You can send more bits at once, or you can send bits faster. SerDes takes the second approach. For example, instead of using 8 traces each running at 1 gigabit per second to achieve 8 gigabits per second total, you could use a single trace running at 8 gigabits per second. The total bandwidth is the same, but the implementation is very different. This shift has several major advantages. First, it drastically reduces the number of pins an IC needs for serial channels, therefore reducing the number of traces required. Fewer pins mean lower costs, simpler packages, and easier board design. Second, it eliminates inter-pair skew. Since all the data is transmitted over a single high-speed path, you no longer need to worry about multiple signals arriving at slightly different times. Third, it improves scalability. It is far easier to increase the speed of a small number of high-performance serial links than it is to keep adding more parallel traces. This is why SerDes has become the foundation of nearly all modern high-speed communication systems. If you've ever used PCI Express to connect a GPU or an SSD, you've used SerDes. If you've used Ethernet to connect to a network, that's SerDes. High-speed USB links also rely on serial communication. In fact, most high-speed digital interfaces today are built on top of SerDes technology. But there's an important detail we haven't discussed yet. Sending data at very high speeds over a single trace introduces its own challenges. Signals become distorted, timing becomes harder to recover, and the physical channel starts to behave in non-ideal ways. So while SerDes solves the scaling problems of parallel interfaces, it creates a new set of engineering challenges that we need to address, and that's what the rest of this course is about. We're going to look at how a SerDes system is built, how signals move through it, what goes wrong along the way, and how engineers design systems to ensure data is transmitted reliably at very high speeds. To summarize what we covered in this video, parallel interfaces are simple but don't scale well due to pin count, skew, and power limitations. SerDes replaces many slow parallel traces with a small number of fast serial links. By trading physical area for speed, SerDes enables the high bandwidth communication required by modern systems. Now that we understand why SerDes exists, the next step is to look inside a SerDes link and understand how the transmitter, channel, and receiver work together to move data from one side to the other.